Hello, welcome back to Piers Rocks. Today I'm introducing the software defined retro ROM. I think this is the most flexible replacement retro ROM there is. One of the biggest frustrations I faced getting into retro computing is that I've hit a lot of failed ROM chips in my machines. And ROM chips typically come in three different flavors in the machines of the era that I'm working with. There's 2364 ROM chips, which are 8KB ROM chips with one chip select line. 2332s, this is an example of a 2332, which is a 4KB ROM chip with two chip select lines. And 2316, which is a 2KB ROM chip with three chip select lines. Now, chip select line is how the system indicates to a particular ROM or RAM chip that it should be active, that it should look at the address lines and place data at that particular address within it on the data pins. If you had more than one of those chips selected simultaneously, they'd both be writing to the bus and garbage would result. The chip select line behavior was mass programmed at factory, so they could either be active low or active high. And each different chip select line on the 2332 and 2316 could behave differently, so you could have any combination. That means two different chip select combinations on the 2364, 4 on the 2332, and 8 on the 2316. Now I've got some typical ROM replacements in front of me, and these are all 2364 replacements, which is what I had to hand. And while these all have a bunch of jumper settings, the jumper settings on these are to allow you to select a different ROM image. So each of these allows you to store multiple 2364 and 2364 only ROM images on the chips that are on board them, and you can select between them with the jumpers, but you cannot change the 2364 chip select behavior with these boards. You can buy boards that allow you to change the chip select behavior of the replacement board. Those are typically implemented using a one or more NOT gates on the replacement board itself, and either use additional jumpers or hardware links that you solder up with, say, 0-ohm resistors to permanently change the chip select behavior of that replacement board, which means you can have multiple different images of that type and that exact chip select behavior on the replacement board. But if you want another chip select behavior, essentially you need another board. That's pretty inflexible. So the second issue I have with common ROM replacement boards is that they're tedious to reprogram. We look at this replacement board as an example. This is probably the most common type of ROM replacement boards. It uses an old stock 27 series EEPROM, and the replacement board essentially just maps the 28 pin down to the 24 pin. To reprogram it, you have to remove this from the host. You then have to remove this chip from the replacement board. You then have to put this into a UV light source for a couple of minutes to erase it. Then you need to put it in the programmer, which will cost you $40 or $50. Then you need to reinstall the chip back in the replacement board and stick it back in your host. That's going to take you 5 or 10 minutes to do. The second board uses a slightly newer and different form factor 27 series EEPROM, but you still have to remove this board from your host. You have to remove the chip from this board. You have to put it in an adapter, and then you need to put the adapter in the EEPROM programmer. Again, you're talking 5-10 minutes of work. And then this third type I came up with, and it uses a brand new flash chip from ST on the underside. But again, this needs to be removed from the host, inserted in a programming jig, the programming jig put in EEPROM programmer and reprogrammed. So this can still take you a couple of minutes. And every remove, reinsert cycle risks damage to either one of these components or your host system. The third issue I have with the typical replacements is, we'll just look at their size compared to the original ROM chip. This most common example of a replacement is particularly big and bulky, both in the XY direction, but also height-wise. It's very substantially taller than the original chip was. But that goes for this replacement type as well. Now, this third example, I came up with a board that was essentially the same footprint as the socket that this ROM chip goes into. And I was able to do that by using this surface mount flash part on the underside. But this still has the problems of inflexibility and also being quite tedious to program. So here's my software-defined retro ROM replacement. And this is essentially ultimately flexible because it's fully implemented in software. It can implement any of the different ROM types, 2364, 2332, 2316, any of the different chip select behavior combinations, and it can do it differently from multiple images that are all stored on board this chip simultaneously. So you can select between different images using the jumpers on the top, and they implement different ROM types and different chip select behaviors under the covers. Programming of this is much easier than the existing solutions. So there are 5 programming pins on the bottom here, and normally you only need to connect 3 or 4 of these pins to reprogram the device. And if you want to, you can reprogram it in the host. So you don't need to remove the chip, reprogram it and replace it. You can leave it in the host, leave the host turned on, and just reprogram this device in situ, which massively reduces the physical stresses on both this device and your host system. So I designed this to be as compact as possible, and it's very close to the footprint of the original ROM, and it's identical to the footprint of the original ROM sockets. This solution is pretty cost effective. It uses a $2 microcontroller from ST, it uses a 10-cent voltage regulator, and then a handful of passives plus some header pins. The PCB is two-sided, and all the components are on one side of the PCB, so it's much cheaper to have the board manufactured than a more complex design. Finally, the hardware design and all of the firmware and tooling required to build and flash your ROM images is open source. Demo time. Here's one of my Commodore 64s. It has one of the more traditional ROM replacements in it. You can see it's running a custom version of Jiffy DOS at the moment. I'm going to turn this off. I'm going to remove the kernel ROM. Put that out of the way. And I have the software-defined retro ROM here. It has a number of different C64 images on it. Because I haven't fitted any jumpers at the top, it will load ROM image 0, which is a stock C64 kernel. So I'll install that, turn the machine on. Hey presto, it boots and it runs perfectly stably. Next, let's try something a bit more interesting. I've got the standard Commodore 64 dead test ROM installed on this software-defined retro ROM, and it's image number 3, so I'm going to set the jumpers to position 3, and I'm going to turn the machine off and turn it back on again. Now this image is normally installed on a cartridge, but it will run as a kernel ROM. That's what I've got installed here, and it takes a little bit longer than a standard kernel to start up and initialize the display, but you can see it's initialized the display and it's now running the tests. So far we've seen software-defined retro ROM acting as a 2364 replacement. The character ROM on this C64 is a 2332 with 2 different chip select lines, and I have the character ROM image already on software-defined retro ROM in image 2. So we'll swap it over from the kernel socket to the character ROM socket, and we'll reinstall the Jiffy DOS kernel in the kernel socket. I'll remove the character ROM. I'll swap over software-defined retro ROM. In he goes. And I'll put the Jiffy DOS kernel ROM back in. As you can see, this is actually a switchable ROM. And then turn the machine back on. And we see it boots fine, and in particular we can see the characters on the screen. I'm now going to reprogram the software-defined retro ROM while it's installed and running as the character ROM in this C64. So I've got just a standard SWD programmer hooked up to it using 3 wires. This is actually a Raspberry Pi debug probe that I'm using. And off camera I'm going to kick off a rebuild of the firmware image, and then it will erase the STM micro and reprogram the firmware. After that, the STM is going to reboot. So while it's erasing the micro and while it's reprogramming it, we'll see garbage on screen because it's no longer providing the characters for the VIC chip to display on the screen. But as soon as it's rebooted and started serving the character ROM, we should see the display come back. The bulk of this time is going to be actually downloading the images from zimmers.net to put in the firmware image. So that's happening now. Now it's erasing and programming the STM. So it's erased, it's doing programming, it's nearly done, and there we go, it rebooted, and it's now reserving the character ROM. Now let's prove this is actually a software implementation. I am going to rebuild the firmware again off camera and change the frequency of the microcontroller. Right now it's running at 100 megahertz, which is about what's required for the character ROM on the C64. I'm going to drop the frequency of the micro down to 80 megahertz. It will not be able to serve the character ROM bytes fast enough for the VIC2 chip to refresh display. So we'll see some weird artifacts appearing as a result of that. So it's downloading the images again, it's building the firmware image, it's erasing and programming, and it's done. Right, so we're seeing a whole bunch of weird artifacts on the screen. That's essentially because in a whole bunch of cases, the software-defined retro ROM is serving the byte just a bit too late, just outside of the timing specification for this ROM type. That's with an 80 megahertz. Now let's rebuild it and flash it with a frequency at 85 megahertz. And because the clock speed of the STM micro is faster, we'll see fewer artifacts on the screen. So it's downloading the firmware images, it's now erasing the micro and reprogramming it. And there we go, we get fewer artifacts, but we still get some artifacts because it's not able to keep up. As the final part of the demo, I want to show you how you can go about building your own firmware images and how you go about flashing them onto the software-defined retro ROM. So here I have a config file for the software-defined retro ROM, and you can see it's got this ROM configs variable in it. And this is for a VIC-20. You can see the format is pretty straightforward. You have a series of entries for each of the ROM images you want software-defined retro ROM to serve for you. And you can provide in a file name. Here I'm providing a URL, so the build process will download that binary file dynamically. A type, here the kernel on the VIC-20 is a 2364, and the chip select behavior. So there's only one chip select line on 2364, and for this type of ROM it's active low. Perhaps more interesting is the entry for the character ROM, which again has a file type, which is a URL. Could be a local file if you have local files to build into the image. Type is 2332, and there's two different chip select lines, and their behavior is configured. Now for the character ROM for a VIC-20, the chip select line behavior is different than the C64. So on the C64, CS2 is set for 1 in the config file. Some other things you can do in this config file, and most interesting probably, is that if you have a zip file, if you're downloading a zip file from a URL, you can actually provide the build process with a file name within that zip file to extract. Some of the firmwares up on places like Zimmers actually zipped up. Now let's see how you actually go about building the firmware. You need to pass in an environment variable for the type of STM chip you're using. Here I'm using an STM32F411RE. You pass in the config file, the one we just looked at, and then you make run. And this is going to do everything. This is going to download all of the ROM images from the sources that you provide. It's going to build the actual software that serves the ROM images. It's going to package all of that together in a firmware file, and then it's going to erase and flash this device. Once that's done, I should be able to reboot the VIC-20 and it should boot up. So it's downloaded the images, it's building the firmware, it's erasing, and it's programming, and the whole process takes about 10 seconds. And now it's ready to serve that image. So if I reboot the VIC-20, it should now boot. There we go. It's booted with the stock VIC-20 kernel. The final demonstration I wanted to give you with the VIC-20 was nothing really to do with software-defined retro ROM, but there's a dead test cartridge image for the VIC-20 that's open source. It's not designed to run as a kernel ROM image, but I've ported it so it does run as a kernel ROM image. It's part of my stock VIC-20 software-defined retro ROM firmware. So if I add image select jumpers to jumpers 1 and 2, that selects image 3, which is where it's installed. If I reboot the VIC-20 now, it should boot up with the dead test program running. There we go, we've got a different border color. It's running all of the different dead tests. As I said earlier, everything here is open source. All the firmware is open source, and all of the hardware design files required to have a PCB manufactured are provided as well. In terms of BOM cost for this, I think if you're making these in a quantity of 3, you can do it for $5 a piece, and it'd be much less if you're making these in any sort of larger quantity. OSH Park will manufacture 3 of these boards and ship them to your door for $4.60 at the moment. The STM microcontroller will cost you around $2 from AliExpress, depending on the exact model you choose. The voltage regulator will cost you about 10 cents each, and the capacitors and resistors cost pretty much nothing, and then there's a few header pins required as well. So as I say, $5 BOM cost is very achievable and will be much lower if you're doing that in any quantity. I hope you found that interesting and useful. If you want to find out how I met seemingly impossible nanosecond access times in software, join me next time. Till then, rock on.